In section 1 of chapter 3, we're going to be looking at our first way to solve what are called linear systems, and that's going to be by graphing. When we have a system of equations, what that means is we have more than one equation, and those equations will have then more than one variable in them. We're going to begin with systems of two equations, which will then have two variables. However many equations there are should be the same as the number of variables that there are. So if I wanted to solve for 50 different variables, I would need to be working with 50 equations at the same time. We are not going to be there. Okay, we're going to start with systems of two equations and two variables. A solution is a ordered pair that works for both of the equations, or if we're working with more than two, that works for each and every one of the equations. So it has to be something that makes them all true. It is not enough to just make one of them true. To solve by graphing, we are going to graph both of the equations on the same set of axes, and then the point that would make both of those lines true would be the point that they share, or the place that they intersect each other. There are three different things that can happen. They can intersect at one point, and then we're going to have one solution. It could be that when we graph them, they actually turn out to be the exact same line, which means that anything that works for one of the lines would really work for both of the lines. So there are infinitely many solutions then because a line goes on forever. Or it could be that when we graph them, they actually turn out to be parallel to each other. And those lines will never intersect each other, so there's no solution to that system. When we see something like this happen, we would want to confirm that they are actually parallel, not just that they look like maybe they are. And the way we tell if we have parallels, we learned back in the last chapter that parallel lines have the same slope. So we want to confirm that the two lines have the same slope. Because if it's slightly off, they might not look like they're going to intersect, and they might not intersect anywhere close to where we're graphing. But if they are just slightly leaned in towards each other, then eventually somewhere out there, there would be a point they intersect. So we want to confirm they are actually parallel by checking their slopes. Is there a question?
It says one of the solutions is intersect at one point. Is that like the normal?
Yeah. So that would be like the normal. I've just got two lines. They come together. They meet at one point. And that's what we're going to see most of the time. Is that our two lines are just going to intersect each other at one point. Our first type of problem says to check whether the point is a solution. This has an A and a B. There are two different ones. What we do to check and see if it is a solution is we plug it into the equations. It must work for both of the equations to be a solution. Working for one is not good enough. So I'm going to start with the point 2, 2, or A. It says plug in the point 2, 2. If I plug that into the first one, I get 6 minus 4 equals 2. That works. If I plug it into the second one, I get 2 plus 4 equals 6. That works. So that means that 2, 2 is a solution. It works for both. For part B, if I plug in the point 0, negative 1, I'd be plugging in a 0 for x and a negative 1 for y. If I plug that into the first equation, I get 0 plus 2 equals 2. And that works. If I plug it in the second one, I get 0 minus 2 equals 6. And that does not work. So that is not a solution. Okay, even though it works in the first equation, that's not good enough. It has to work in the second one as well. Our hope, kind of like our best case scenario in these problems, is if you plug it into the first equation and it doesn't work, then you don't even have to bother checking the other one. So that's kind of like a time and work saver. If you can plug in the point and it doesn't work into the first one, you don't even have to bother with the second one because it has to work for both to be a solution. Okay? Questions? Go ahead and try these two. Okay, so for the first one, I'm going to plug in the point 1, 4 to the system. If I plug in a 1 for x and a 4 for y, I get one that doesn't work right away in the first equation, and that's awesome. That means we don't even have to bother checking the second one. That's just a no. Right, straight up, if it doesn't work in the first equation, it doesn't matter whether it works in the second equation because it has to work in both to be an answer of yes. When I check the point negative 5, 0, I plug that in the first one, I get negative 5 plus 0 equals negative 5, so that works. When I plug that in the second one, I get positive 10 plus 0 equals 10, so that works, and that one is a yes. Okay. It is possible that both of the points could be yeses. It is possible that both of the points could be no's. So don't just do the first point and then assume something about part B. Okay. It's possible that they could both be solutions. It's possible that neither one of them could be solutions. Questions on checking solutions?
On our homework, can we just write yes and no?
Yep. Okay, to solve a system by graphing, what we want to do is graph each of the lines on the same grid and look for the points they share. They could end up being the same line, which would mean they share all of their points. They could end up just crossing, which would mean they share 1 point, or they could be parallel, which means they share no points. But we want to start by graphing them. I'm going to graph the first one in standard form here. I use the cover-up method. So if x equals 0, y equals, and I solve for y, I get negative 1/3. Okay, so that was our cover-up method that we learned earlier this year, where I just let x be 0 and that eliminates the x part of the equation. I get negative 3y equals 1, so I can just solve for y. Or if I let y equal 0, then I get 2x equals 1, so x is 1/2. I'm going to plot those points out. Y is negative 1/3, x is positive 1/2. And then I want to draw as straight of a line as possible here, which for me is a big, big challenge. I'm not very good at drawing straight lines. The second one is also in standard form, so if I let x equal 0, I get that y is 3. And if I let y equal 0, I get that x is 3. So those both have x-intercepts and y-intercepts of 3. And that one I can draw a pretty straight line because that one has a perfect slope of 1, so I can just kind of connect the corners of those boxes. Now what we're looking for is where these two lines intersect. Now in this problem, they're intersecting kind of floating out in the middle of a square. That will not be true of your homework problems. That means my graph is kind of imperfect. So what we need to do is try to locate the point where we think they actually intersect, and then we want to test it and see if that's the point that works. So they intersect the closest to right here. So I'm going to start with that being my first guess. Because there's some imperfection in the graphing, it's a little bit off, but I'm going to say maybe that's my point, which is at 2, 1. And I want to test that now and see if that point works in both of these problems. So if I plug it into the first one, I get 4 minus 3 is 1. That's good. If I plug it into the second one, I get 2 plus 1 is 3, and that's good. So that means that that is the correct solution then. Graphing on graph paper will be helpful for you, and being as precise as you possibly can will be helpful. So like using rulers and stuff like that will help you make straighter lines, which will help you make better guesses. Okay. So we graph each line, look for where they cross. They should cross at some nice whole numbers for you. So pick a point that would be a good intersection point and try it out and see if it works. If it doesn't, then try another one. Maybe you're a little bit off the other way. Questions? Alright, so for this one, our first one again is in standard form. So if I let x equal 0, what do I get for y?
0.
In the first equation, if x is equal to 0, what is y equal to? 4. And if y equals 0, what is x equal to? Negative 4. So I get a y solution of 4, an x solution of negative 4. And I want to connect the dots there. And this one has a nice slope of 1, so I can easily connect the dots there. For the second one, if I let x equal 0, what do I get y is? 2. And if I let y equal 0, what do I get x is? 2. So I get solutions of 2 for both of them.
I don't get how you get the second and
So I get what?
third. The 7 or 6 right? Like how do you get the 2?
By solving. If I plug in a 0 for x, what do you get for y? And then if I plug in a 0 for y, what do I get for x?
Oh, 2 equations.
Yeah, yep, we're graphing 2 different equations. So the first one, we get one set of points the same when we get another set of points. Then we want to look for what these lines have in common, which appears to be this point, which is at -1, 3. But you would want to confirm that and make sure it does actually work. If I plug in a -1 for x and a 3 for y in the first equation, I get -2 minus 6 equals -8. That's good. If I plug in a -1 for x and a 3 for y in the second equation, I get 4, which is good. So that means that our solution is -1, 3. Give your solution as an ordered pair, x comma y. Questions? Okay, for the first one here, if I let x equal 0, what do I get for y? -3, and if I let y equal 0, what do I get for x? 2. So I can plot that out. Y is -3, x is 2, and connect the dots with as straight of a line as I can manage. For the second one, if I let x equal 0, what do I get for y? -3. And if I let y equal 0, what do I get for x? 2. If I plot those out, they are actually the same point, so I get the same line. So it turns out that these were actually exactly the same line, which means that any point that one of them touches, the other one touches as well, and all of those points are solutions. So what we do is we say there are infinity many solutions. Anything that's on that line is a solution, and there's no possible way to list all of the points on that line because lines go on forever and ever, and they get every single possible fraction in between. So if we graph and we get 2 lines that are exactly the same, that means anything on that line works, and the solution is infinitely many solutions. Anything that's on that line is actually true. Questions? All right, so for the first one here, if I let x equal 0, y is -3, and if I let y equal 0, x is
-1.
2. So I get y is -3 and x is 2.
Oh, it's the same thing as last time.
That is the same line as last time. I was not feeling extremely creative when I wrote this lesson. For the second equation, if I let x equal 0, what is y?
-1.
-1, and if I let y equal 0, x is 2/3. So I get solutions of -1 on the y and 2/3 on the x. And what appears to be the case?
They don't touch.
It appears that they're parallel and they're not going to intersect. We want to actually confirm that because maybe they are slightly leaning towards each other and they will intersect somewhere. The way we confirm it is by checking slopes. So for the blue line, if I do a rise over run, I get a slope of what? 3 over 2. For the purple line, if I do a slope, I get a rise of 1 and a run of 2/3. So I then have 1 divided by 2/3. How do I divide by a fraction? Multiply by their reciprocal, or in a calculator, you could do the division and just put parentheses around it, and that would work out as well. And I get 3/2, which is the same thing. That means these lines have the same slope, which means they are in fact parallel and they will never touch each other. So that means that there is no solution to this system. You do want to actually confirm they are parallel because it could be that they will intersect and we're just not seeing the intersection. Okay? Questions? All right, so as your homework, make sure you notice you've got some multiples of 3 in there.